So the first thing we're going to do will be to implement this model in Excel. Okay, and we did have this investment problem formulated last time from the class, and this shows the complete model. And if you go to your Moodle, here, week 3 class resource to download this data and open it. To save some time, I already put those data in this spreadsheet, so you don't have to input it. In my undergraduate class, I do ask the student to input the data because they make mistakes when they input the data, and we check the model all around and say there is no mistake in the model implementation, and they found, oh, they input like 8.65 differently, and that's why the solution is wrong. So that's something just for you to be cautious. When you implement those data, make sure you check them, okay? Because it's really hard to check a model if it's wrong later, okay? So these are the data I put, so that's the 3.9, and just briefly review what we implemented. So this is that investment problem that the client of investment company is trying to maximize the return from 6 different bond issues, okay? And they had some constraints. For example, like any of them should be no more than 25% of the total money invested, the long-term ones, the high-risk ones, and the sum need to be this much. Okay, so now let's go to that's Excel. What I inputted here, this table here, are basically what you see from that problem statement. Okay, so from that problem statement, these are all given. Okay, and we know that the decision variables I don't know how to. So let's insert a line here. Oh, sorry. Click Enable Editing so you can edit it. Okay. So first I'm going to insert a column here to reserve those cells to be my decision variables. Okay, remember those decision variables? How much to invest in each of those bonds, right? So since all those bonds are listed here, so a natural place to put the decision variable will be here, okay? And we'll shade them in yellow. And give it a meaningful label, a heading. So money, amount money to invest. So these will be our decision variables, the ADEMOS. Okay. Then let's go back to look at our objective function. Our objective function is to maximize the return. Those are the sum product of our return rate and the decision variables. Okay. So we go back to see, okay, the total return, and we have those return rate here. And we know that the objective function would be just the sum product of this column and this column here. Okay, and I'll put it here, total return equals to be sum product of this column and this column here. Okay, highlight this in blue so we know that's our objective function. Okay, so we took care of the decision variables and the objective function. Now let's check. The first constraint represents the one that's no more than 25% should be invested in any of the investment. Okay. Then here in this slide, I put all the constraint in like one formula. But remember when we formulated in class last time, we had 6 formulas, right? So that's A less than equal to 25% times this 750,000. So we have one for each. And so we have the left hand side here, right? The A through S here. We need, and we said we need to have these 6 formulas here. So we have the 6 left hand side. So it's natural we just create another column here to be the right hand side. So when we go to define the constraint, we can have just like this entire column being the left hand side, less than equal to, then another entire column, the right hand side. Okay. So for that, I'm going to insert another column here and change the, oops, sorry, not the entire column. Okay, so that will be, and in this column, what I want to calculate is the 25% multiply, that's 750. Okay, 750,000. So instead of put here, okay, so equals to be 0.25 times 750,000. Instead of putting this way, we said we don't embed those numerical values in the formula. Okay, so I want both number to be somewhere. Okay, so instead of this way, I'm going to put here. Okay, so maximum percentage. Okay, and here I'll put 25%. So later I can refer to this cell in my formula. And I do need the other 750. Okay, so here first I'm going to move this. Okay. That's a 750,000, right?
Can you check it?
Check what? No, this one probably I just type it. Maybe I typed one more zero or not. Yeah, there is one more zero here. Yeah, that's for demonstration purpose. I'm not going to use it. Okay, so I'm going to put that 750 here. The total available. That's the 750,000. So why I put it here? Because that's the sum of this entire column. So we said that things that are logically related need to be physically related. So I put this value here. Okay. Then here I'll just put the formula that equals to be this 25% multiply this 750,000. And I'm going to copy this formula all the way down. And I don't want either cell to be shifted when I copy it. So click in it. Then you can just press F4 until you get it. Okay, so here also click F4. So the dollar sign will appear on both the row number and column number. That means the entire cell is fixed. Okay. Now you can copy this formula all the way down. And that's my first constraint. That's the right hand side. So I just shaded this one. Here, I'll shade it in this way. I shaded it so that I remember there is one constraint here. Okay, so we took care of this first constraint. Setup. Second, do you guys remember what are these representing? What's that? Remember what do they represent?
The sum of investments higher than 10% maturity, I think. The investment that mature
10 years, more than 10 years.
or
Okay, okay, so these represent the long-term bond. Okay, those are the long-term bond that matures more than 10 years. Okay, so that's A, D, M, and S. So one way we can do is, okay, put a cell and, you don't need to follow here. Okay, put a cell and make it equal to A plus D plus M plus S to be the left-hand side of that constraint. And, oh, sorry, did I move it? And then put another here equals to be like, is that the 35%? No, 5%. So put the 50% equals to be 0.5 times this is 750 here, and then make it one constraint. Okay, so that's one way to do it, but that's not the preferred way. Okay, because we want our spreadsheet first, you can trace it back. To know what are included here, you have to click inside, say, oh, that's the sum of these ones. So that's not preferred. Second, we want our spreadsheet to be modifiable. For example, later, say, another long-term bound, and one of those bound, say E, become long-term bound too. Okay, it matures more than 10 years. Then you have to go click inside this cell and click, okay, let's add one more here. Okay, we don't want to do this. We just want, okay, once there are changes in those maturity year, I just come here, change this to 10 year. Then my model will be automatically updated. Okay. So let me go back. So what should we do? We're going to put, insert a column here. To say, okay, is that long term or not? And we'll use 1 to represent yes, and 0. Oh, sorry. 1 means yes, and 0 means no. Okay. Or you can put, I use that 1 equals to be yes, and 0 means no. Okay, and then I guess most of you know there is an if function in Excel. Okay, so you can just type here to be if. So there should be a logical test. Logical test will be if this value is greater than 9, which means greater than or equal to 10. Okay, then output is 1, means yes, it's a long-term bound. Otherwise, 0. Okay, so in this way, we create a formula that first can be copied all the way down. Second, you can modify just the value in the years to maturity, and it will be, you don't need to change anything here. Okay, any question? No? Okay, then you can see, okay, this is mature in 11 years, it is a long-term bound. Then copy this formula all the way down. Click inside to check whether it copied correctly. Okay. So it look at this value here. If it's greater than 0, then return 1, otherwise return 0. Okay, and we do see there are 1, 2, 3, 4 long-term bonds that corresponds to A, D, M, and S.
Do we want to define what we consider long-term? So if they decided 9 years is long-term, or 10 years, or 15?
In the problem it says.
It says.
Yeah, more than 10 years.
Okay.
Yeah, if you look at the problem statement back.
I'm just wondering why we were defining the 9 as a.
Oh, because I use greater than. Okay. If you use greater than equal to, you put greater than equal to 10.
But I'm just asking why we didn't set a cell that had the value of 10 in it somewhere, and then you reference that cell.
You could do that?
Yeah, you can. You can.
I was just curious, it seemed like
I
we
see.
talked
So
about
what
doing that
Caleb is
before.
suggesting is saying that you put, say, like the definition of long term equals to be 10. So you say like if this cell is greater than that cell containing the 10 value.
Exactly.
Okay, okay. Yeah, okay, yeah. You can go all the way to those details.
Okay, I was
Yes.
just curious if that was something we had to do or not for.
I
not
think
reference.
probably will be good.
Okay.
That's good. Yeah, yeah. To save some time here, we don't do it now. But yeah, that's a good point. Okay, so those are the long-term ones. And so instead of putting, so this equals to be this plus 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 plus. Here we're going to put, okay, total, long-term total. Here, we can just use that the sum product function again. Okay, yeah, so another good thing of using this 1, 0 is that you can cancel off those short-term bounds when multiply this value to this 0 here. Okay, so you put sum product of the decision variables and those 1, 0 value here. Then you are just summing up those long-term ones because they have a coefficient of 1 and the other ones have coefficients being 0, and that 0 multiplied this decision variable will cancel that value off. Okay, so with this function we calculate the sum of long-term ones. And going back to that constraint, we know that the sum of the long-term one should be greater than or equal to 50%. So let's put so it should be 3 required, and this value should be that 7,000 times required. I'll put just a print. Oh, sorry, just put 50% here, and use this value here to multiply 50% to get half of this 750,000. Oh. Okay, so that gives you that value. So later we know that, so that will be the left hand side, this will be the right hand side of that constraint. Okay, so that takes care of the second constraint. Now the third constraint are the ones that are riskier ones, should be no more than 35%. Okay, and the risky ones are defined using the rate. Okay, if we go back to the problem statement, see what they talk about here. Okay, represent the highest risk if they were rated lower than a very good. So if we check lower very good, so very good is a 1. That means if they get a rating here being 2 or 1, then those are the riskier ones, right? Okay, so which ones are that? Is that lower than very good? Is that that's D, E, and O. So D. That's. Oh, sorry. You see, they rated from the other way. It's like 1 is excellent. Okay, so actually it means the value should be greater than 2. Because 1 is excellent and very good is 2, good is 3. Okay, so that means for any of those bounds that the rating is greater than equal to 2. Greater or equal to 2. So 2, 3, 4. Okay, so if they get the 2, 3, 4 ones, then they are that we get lower than. Oh, okay, just greater than equal to 3. Okay, so it's greater than equal to 3. So it's this 3, 4, 3. There are 3 of them. Okay, So let's just define that. So with this setup here now, I want you guys to set this column yourself. Okay, so would it be risky or not? So 1 means yes, 0 means no. Okay, so
If it is yes, so this means that the rate is excellent and good. So if it's low risk,
no, the riskiest ones.
oh,
The good, the one that's worse than good.
excellent or risky.
No,
So
the
that's
good,
low risk.
fair, I think it's lower than the very good. Go back to here again. Here. If it's higher than 2, which means they are the good and the fair. So those are the 3 and the 4s. Okay, so those are the riskiest ones. So the formula would be if this value here is greater than 2, then yes, otherwise no. Okay, so you can see that D, E, and O are selected. That's the same with what we put here, D, E, and O. Okay, so the formula is if this rating value is greater than 2, return 1, otherwise return 0. Okay, so here would be total of high risk account. Then you can just do the same thing, sum product of your decision variables and your 0, 1 column. To add D, E, O together. Okay. Then here we'll say allowed. So required here means at least, and allowed means at most. Okay. Allowed 35% here. So I'll put this equals to be this 750,000 multiply this 35%. This gives us the right hand side of this constraint. Oh, sorry. What's this? Okay, so this takes care of the third constraint. Then we have our fourth constraint, which is the sum of all of them need to be 750, which is pretty easy now. So we'll just find a place to calculate the sum of all of them. So a good place would be here. And I'm going to move this down. So this can be used as our right hand side of that constraint. Okay, so here would be total invested, and that is the sum of all the values here. Okay, then I'm going to highlight these as my constraints. Okay, so I'm going to delete these two cells that I use just for demonstration purpose. Okay, so now we have our.
What's D10 and 11? That's repetitive, isn't it?
Which one?
D10 and 11, what is that?
This is the sum of the decision variables. So that's the left-hand side of that constraint. So what's the actual amount you invest? And this one, you just put the total sum. Yeah. And these two cells represent the left-hand side and the right-hand side of this constraint here. Okay. Okay, so then the last constraint is the non-negativity, and we know we can just check that box in the solver window. Okay. Now with this setup, we're going to go to solver to define it. So go to add-ins. Premium solver. Oops. Click reset all because I think when I loaded this data, this file, I didn't delete all my constraints for you guys. Okay, so now it's pretty easy now. Add your variables. So all those yellow shaded cells are the variables. Click OK. I think like in a few of your comment, like the suggestions and comments I gave for the optional Excel model, I said like for some of those decision variables, if it's not really needed to separate them, meaning put them in different columns separated by like another row or column, it's better you put them together like this. So when you need to select the variables, you just select the whole thing. Okay. I don't know whether I explain this clear. For example, if you put the A, D, and E in separate cells, for example, if you insert, say like there is something else that separates the cells that contain your decision variables. Then when you select them, you have to select this one and put a comma, and then select these ones. You won't be able to select all of them together because there is a cell between them that does not represent decision variables. So unless necessary, we usually put your decision variables all together. So when you select them, you don't have to select them several times. Okay, so now the decision variables are already selected. Oh, sorry, objective. That's here. And make sure, okay, this is maximization, so default, that's correct. Then add the constraints. So we know that the first constraints, first group of constraints are these ones. Each of them need to be less than or equal to the 25% we calculated here. Okay, so that's the first constraint. Click add. And the second constraint, that what we did is the long-term ones. So the long-term ones need to be greater than or equal to, because it's required. You have to have at least 50%. So make sure you change the sign. Right hand side. Okay, second constraint done. Third constraint. High risk ones need to be less than or equal to 35%. Calculated here. Then add another one. Total invested need to be equal to 750,000 here. Okay. So this model we implement the one that we assume will invest all the money. Okay, so once you are done, click OK. Make them non-negative. Change your program to standard LP. Okay, make sure you don't miss this last step.
So simplex.
simplex. Okay, and then solve. Okay, you guys get the same result? No? So if you get the same, then just do some cosmetic work. For example, put this thick bottom border through all the and here. And if you get different now, take a look. Same here. Okay, and then I would highlight these using bold. Same here. And I'm going to put a border, put a special border around my decision variable, the objective function. And these ones bold. These ones bold. Okay, and for those values that represent currency, I'm going to change this setting to currency. Same here, here, here. Okay, good. So highlight all of them. Go to number, currency. Click. See, there are a lot to learn too for Excel itself. Okay, here. Okay, so I'm going to put all of them to be middle alignment. Okay, and clear here like this is not shown, so I'm just click here. So the entire heading is shown. And yeah, so that's the model for this problem. Okay, so the main thing we talk about is to use those the if function to represent this one long term or not, high risk or not. Use 1, 0 to represent, and the benefit of that is later we only modify here and we don't need to define other places. And also those 0, 1 value gives us enable us to use the sum product function to add just those values that we want, using those zeros to cancel the values that we don't need to add to the total sum. Okay, and here, yeah, these are all bold, so about this. Okay, so save this just for yourself, and we're going to talk about more model formulation now. Okay, so let's do this one quickly. This is a pretty easy problem. 3.11. If you still have the printout you got from last week, you can use that one, or you can just read from here, the problem statement. So that's 3.11. in my version. I'll give you some time to read the problem statement first, and then we'll formulate together. This is a relatively simple simple problem. Okay, so we'll just formulate this quickly. Okay, so I think you guys finished reading once. Okay, and we'll talk about the problem together. So basically, in this problem, the first paragraph is all about some general information. Okay, that probably has very little to do with our formulation. Okay, and it tells you that in those mix, they usually so this company has 4 types of feeds. That's specified here, feed 1, 2, 3, 4, that contains different percentage of those corns, grains, and minerals. Okay, and the cost per pound for each of those feed differs too. And again, then on average, so this is the general information. Again, general information. We don't probably need to use it. And chicken growers must ensure that they feed the required nutrients to their flocks in the most cost-effective manner. Okay, so that probably indicates something for us. And AgriPro has just received an order from this local chicken farm for 1,000 pounds of feed. Okay, and they want this feed to contain at least, okay, I was at, okay, that's a keyword for constraint, at least 20% corn, 15% grain, and 15% minerals. What should this company do to fill this order at minimum cost? How do they fill this order? They put a mixture of this feed 1, 2, 3, 4, and so the total is 8,000 pounds, right? And in this 8,000 pounds, by considering how many feed 1, feed 2, feed 3, feed 4 to put in this fix, they want to make sure that at least 20% of this 8,000 pounds is corn. Okay, and 15% of this 8,000 is grain, and 50% of this 8,000 pounds is minerals. Okay, so let's think about what's the decision.
How much or what percentage of
Okay, it's very similar to that investment problem, right? So it's kind of like the same, it's a portfolio. So in that portfolio, it's like how many money you put in each of the bond issue. In this one, it's how much you put in each feed. Okay, feed 1 through 4. It's kind of like a feed portfolio here. Okay, so that's the decision, how many pounds to put in this total mix. or you can use percentage again. Okay, but we'll just use the pound. It's more straightforward this way. Okay, then that's our decision variables, and that's our decision. Okay, then what about the objective? We highlighted something here, right? Yeah, we want to do it the most cost effective way. That means we want to minimize the total cost, and that's because the cost varies by meeting. So if there is no requirement for those percentage, we'll just put feed 4 because that costs less money. Okay, but if you look at that, the corn and the grain percentage is pretty low here, 10%, 10%. We're not able to fulfill these two requirements here, so we have to put some from maybe here or here. Okay, so then let me go to the next slide. So I summarized those key information here. So an order 8,000 pounds. These are the requirements and these are the given information. As we just said, the decision variables will be, so I'll just use F1, F2, F3, and F4. Oops. To represent pounds of feed 1, 2, 3, 4 to put in the mix. Then our objective function is to minimize the total cost, which is pretty easy for you guys now. Okay, so it's the unit cost multiply the pound and you sum them together. So, oh sorry, I have to put we want to minimize total cost, so it would be 0.25 F1 plus 0.30 F2 plus 0.32 F3 plus 0.15 F4. Okay, so that's our objective function, minimize the total cost. Subject to constraints. So we're going to do that in this order here. Okay, so the total order is 8,000 pounds. Okay, that means sum of your F1, 2, 3, 4 need to be equal to or greater than equal to 8,000 because we define them as in pound. Right, this sign doesn't matter. We put greater than equal to or equal to, when it's calculated it will be the same because we want to minimize the total cost. If we can fulfill the order by just fulfill 8,000 pounds, then it will just fulfill 8,000 pounds. It won't go beyond that. Okay, but as we explained last time, we put greater than equal to make it less restrictive, so it's easier to find it. It's more possible to find a feasible solution. Okay, and then we'll look at here. Want this feed to contain at least 20% of corn. Okay, so that means, okay, if you get F1 pound of feed 1, that will give you 30% times F1 pound of corn. Okay, plus all the corns that you get from the other 3 feeds. So all the corns you get from these 4 feeds should be at least 20% of this 8,000 pounds. Okay, the one thing is that we mentioned that last time, we want the units on both sides of the constraint to be the same. Okay, so 30% of F1, that's the pound of corns contained from this feed 1, plus 5% of F2 plus 20% of F3 plus 10% of F4. So that's corn. Okay, so that's the total pounds of corns. Should be greater than or equal to, you want at least the 20%. So 20% times 1,000. Yeah. Yeah, if we define the greater than or equal to, it should be sum of F1, F2, F3, F4. Okay, but we know that it's the same. So let's just, yeah, so for accuracy, just eliminate this. So our model is simple. I'm glad you remember that. Okay, so that's this will be corn measured in pound again. So we check the unit on both sides. They are both a pound of corns. Okay. Oh. Now you can do the same for the grain and the minerals. I'll ask you guys to do that first, and then we'll talk about it. Okay. So do the grains and the minerals. My handwriting looks really naive on those tablets. I think I write much better on paper. It's like maybe 12-year-old or even 5-year-old writing. Oh yeah. Okay, so you guys got the same? Okay, so when you look at it, you got the question?
Well, I don't have the same. I didn't do the last one.
Okay. Okay, why?
Because it's not necessary. It
Okay.
doesn't define a bound or the constraint.
Okay, so for the mineral one, right?
You have the mineral one.
Okay, so if we look at the mineral, the percentage contained in all the feed are at least 20%. Okay, and here it requires at least 15%. That means no matter how you mix them, the mineral requirement will be met. Okay, so that means I will still put it here, but that means this is I should test you. What's that? What kind of constraint is this one? I already give you some hint here. Redundant. Okay, that's a redundant constraint. Because it will be fulfilled anyway, with or without it, it will be the same. So this redundant constraint does not play a role in defining the feasible region at all. Okay. So this, oh sorry, just redundant. Oh. Okay. And so besides these ones, don't forget that the non-negativity. So Fi are all greater than or equal to 0 for all I goes from 1, 2, 3, 4. Okay, so that's my last constraint. I don't have enough space to write here. Okay. Just to summarize, so here on the slide I use x1, 2, 3, 4. So they represent the pound of feed to use in that mix. And to minimize total cost, which is some product of the unit cost and the decision variables. And the constraints are these ones, with this being okay, so that's the problem. And for this one, we want to implement here in the class. I'll ask you do the same, follow the textbook to implement the Excel model yourself. Okay. So let's take a 10-minute break. Okay.